Hey, it's Dr. J. We're doing 5.6 now. We're going to skip 5.5. If you're curious, it's a section about statistics. And if any of you are going on to take the course in statistics, all of that is covered in the introduction of statistics. So I'll spare you the homework and lab and all that. And we'll just move on to the topics that are traditionally covered in this course. So the next section is 5.6, ratios and rates. We start off with a definition. A ratio is a fraction of two values with the same units or no units at all. We typically use the words A to B. So that would be A over B. Yeah, so those are your values, A and B. And sometimes instead of using the word 2, we use a colon, which is still read as the word 2. So this also means A to B, which is written again A over B. And we simplify if possible. In other words, reduce to lowest terms. Just like we've always done with fractions. So that's a ratio. I guess we'll just do a few examples of ratios before I give you the definition of a rate. So write each ratio as a simplified fraction. So 30 to 14, or I could say 9 to 24. And really, you can kind of put it on casual mode in this introduction to ratios because you already know how to do all of this. So mainly I'm talking about the vocabulary and the notation. There's not a lot of complicated math in this section. So why don't you just go ahead and put it on cruise control. You have 30 over 14. Make sure you read it in the right order. And then simplify that if possible. So 30 is 15 times 2. 14 is 7 times 2, and so the final ratio is 15 sevenths, or 15 to 7. Okay. 9 to 24 means the same thing as 9 colon 24. They mean the same thing. It's 9 over 24. And again, simplify this if possible. 9 is 3 times 3. 24 is 3 times 8. And you can cancel a pair of 3's. So we say the ratio 9 to 24 is equivalent to the fraction 3/8. Or 3 out of 8. Okay. So these are what we call ratios with no units. So they can have no unit at all. You can also have ratios with units. So I'll give you a ratio that actually has units, something like 10 miles to 120 miles. So in order to be a ratio, they either have to have no units at all or they have to have the same unit. And so the way we write these ratios is we write it as 10 miles over 120 miles. And we treat the word miles like a number. Right? If you had 5 over 5, that would be 1, right? You would cancel that out. And so this is always going to happen with ratios because ratios will always have the same units. And so they will always cancel out. In fact, oftentimes we just skip this step because we know that it's going to end up canceling out. So oftentimes you can just jump from here directly to here if you know that this is going to happen. All right, and now you have to simplify this. So we got 10 times 1 and then 10 times 12. And then cancel out the 10s. And so you get 1/12, or 1 out of 12. Other ways to say this. You could say 1 to 12. You could say 1 in 12. Or you could say 1 out of 12. Those are all other ways to say 1/12. 1 to 12, or 1 in 12, or 1 out of 12. You know, us mathematicians, we love to have many, many ways to say the same thing. I'm just trying to adjust my camera there. There we go. Hey, can you see me? I guess we'll do another one. Might as well. It's the same instructions. I forgot to say terms. So how about $1.80 to 45 cents. Now, because it's a ratio, I can't have one of them be dollars and the other ones be cents. So even though I called this 45 cents, it's technically 45 hundredths of a dollar, right? Which is what we all know as a cent, right? So you wouldn't want to say $1.80 and then 45 cents without the decimal, because then it would technically not be a ratio because they don't have the same units. All right. So that would be $1.80, or 1.8 if you like, over, I'm just going to write it as 1.80, although it means the same thing as 1.8, over $0.45, and then the dollars again will cancel out. So it's just 1.8 over 45. So we're going to multiply the top and the bottom by 100. Because we want to reduce to lowest terms. This is not in lowest terms. So that would be 180 over 45. Which, by the way, you could have done that mentally. Think about this. $1.80 is the same as 180 cents. And then $0.45 is the same as 45 cents. So you could have just jumped right to here. As long as you understand the units are now cents. Yeah, these have the same unit now. They're in cents. Okay. 45 actually goes into 180 4 times. Yeah, if you don't believe me, 4 times 5 is 20, and 4 times 4, 40. 4 times 40 is 160. And so there it is. 160 and 20 is 180. Or you could take out your calculator. And so this ratio is 4 to 1. Yeah, there's an invisible 1 in the bottom down here. This is what we call a unit ratio. Yeah? When the denominator is 1, this is called a unit ratio. Oftentimes with a unit ratio, we just don't write the denominator. So the unit ratio would just be equal to 4 if the denominator comes out as 1. Now, you can still write the 1, right? You can say 4 to 1, yeah? Or 4 out of 1, or 4 in 1, yeah? Or you could just say 4. Okay, I guess one more ratio, and then I'll give you another definition. Actually, I think I got 2 more. I got 1 more with decimals, and then I got to do one with mixed fractions or something like that. Okay, again, the units don't matter. So from now on, if we're doing a ratio and the minutes are the same, we can just cross them out now, and that saves us a little bit of work. 7 to 0.05, or 5/100ths. All right. Now, if there are 2 decimal places, you multiply by 100. If you happen to only have 1 decimal place, then you can multiply by 10. So what do we got? We got 700 over 5, which is, again, another unit ratio. Because 5 goes into 700 how many times? $140 times. I didn't finish this, but 4 times 5 is 20, remainder 0, bring down the 0, 5 goes into 0 times. So when the ratio is, again, a unit ratio, you can just say 140. Maybe I'll do a couple more. I know I keep changing my mind, but I just realized I want to show you an example with tens. So 1.5 centimeters to 2.4 centimeters. Again, they have the same units, so we don't need the units. You know they're going to cancel. 1.5 to 2.4. This time there's only 1 decimal place, so we're going to multiply by 10. Now remember from the previous lectures on fractions and decimals, it's not customized. You know, if one of them has 1 decimal, the other one has 2, then you have to go with the larger one. So whoever has the most. This one, they happen to both be 10, right? But if one of them's 10 and the other one's 100, you can't customize it like that. You have to give them both the same thing. And the reason is you have to be multiplying by 1. That's essentially what this is. This is a special form of 1. So that would be 15 to 24. 15 out of 24. 15 is 3 times 5. And 24 is 3 times 8. So this is not a unit ratio. This is just a ratio. Well, they're all ratios, but this is a very classical ratio, 5/8, or 5 out of 8. Now, the only thing that could get complicated is if I introduce mixed numbers, which I will do now. So let's say 4.5 inches to 12 3/4 inches. Okay. So we got 4.5 over 12 3/4. Now this one's a little tricky. You first have to write these as impropers. So that'll be 9/2. Yeah. 2 times 4 plus 1, 9/2. And then this one will be 51/4. 4 times 12 is 48 plus 3 is 51. Now, you're going to take the denominator ratio. So this is a ratio of ratios. There's a ratio in the top, there's a ratio in the bottom. You're going to take the denominator ratio and bring it up to the numerator and flip it. It's called the reciprocal. And then you write it as 4/51. All right. And there is no more fraction bar. This fraction bar is now 1, essentially. So we just omit it. And we just write 9/2 and 4/51. Now, take my advice, or I hope you take my advice. If you multiply these, you're going to get big numbers, and then you're going to just have to work harder. All right. So don't actually multiply them. Instead, factor them out. The numerator is 3 times 3 times 2 times 2. Yeah, 3 times 3 is 9. 2 times 2 is 4. Okay, I know you probably can't see that. I'll write it up top in a minute. The denominator is 2 times 3 times 17. You might not remember that one, but 51 is 17 times 3. Yeah, it's one of those strange. So let me write it up here so you can see. 3 times 3 times 2 times 2 over 2 times 3 times 17. And now you can cancel some 2's and a pair of 3's. And so your final ratio is 6 out of 17, or 6/17. Okay, that's about it for ratios. It's mainly just a warm-up to get the ball rolling here. The majority of this section has to do with rates. So let me give you the definition of a rate. A rate is a fraction of two values with different units. That's a rate. A fraction of two values with different units. So, what are we up to? 7, 6, 1, 2, 3, 4, 5. I think we're up to 7. I erased the number too soon. So, for example, one of the most familiar rates that you've heard of, that you use all the time, is speed. Yeah, speed is a rate. So, for example, express the rate as a fraction reduced to lowest terms. So suppose you go 91 miles. Sorry, not 91 miles. 910 miles in 21 hours. So that would be a rate. Now, let me go ahead and do this problem, and then I'll talk about the word in, because it's not always going to be in. So let's go ahead and do it. 910 miles over 21 hours. And because the units are different, they do not cancel. Now you do have to reduce this as much as possible. So 91, I believe, is, what is 91? I just randomly grab this number and let's see if it's divisible by anything. 91 divided by 13, yeah, 7. So that would be 10 times 91. I'm just going to put M per mile. Actually, no, I have to write the whole word. And then I got 3 times 7 hours. So 910 is 10 times 91, but then I need to save some space here. 91 is 7 times 13. 7 times 13. It's another one of those strange numbers. It looks like you can't factor it if you first look at it. I had to actually get out my calculator to make sure. All right. Now, I normally would go a little bit further with the 10, but because the denominator is all odd, there's no multiples of 2 in it, or 5, in fact. I'm not going to bother. I'm just going to cancel the 7s. So the rate would be 130 miles in 3 hours. Okay. So the word in can also mean as per. So you can say 130 miles per, 3 hours. Other ways to say it, you can also say for. So you can say in, per, for. I guess that's it. Yeah, I think that's it. I'm just flipping through all my vocabulary words here. Yeah, that's it. In, per, and for. They all mean rate. Or a fraction, a division, reduced, and then how you say it. 130 miles per 3 hours. Let's try another one. Example 7, example 8. Six calories for 7.5 minutes. This is one that I really need to work on, with my being at home for the last 8 months. I got to track how many calories I'm consuming, or how many calories hopefully I'm burning if I'm out on my exercise bike, which I haven't been using enough. Okay, so we got 6 calories per 7.5 minutes. Now on the homework, sometimes this is like a drop-down menu where you select the right word. Other times, if you don't see a drop-down menu, then you actually have to type the word. And unfortunately, the spelling matters. Although, if it was a test or something and you spelled it wrong, I wouldn't mark it wrong. But on the homework, if you see that you spelled it wrong and it marks it wrong, you could just go in there and spell it correctly the second time. All right, so I'm not grading your spelling per se, but the computer kind of is. And I'm just kind of overseeing it, so I'll just put that out there. I prefer the drop-down menu version, but they're not all like that. Some of them require that you type it. All right, one thing you can do is just kind of ignore the values for a minute, and let's just do the math. Now, don't forget about them, so I'm just temporarily ignoring them. And then now I'm going to multiply by 10, because there's 1 decimal place. Now, again, it's not like the one that has a decimal gets multiplied and the one that doesn't. If one of them gets multiplied, then so does the other. And they have to get multiplied by the same value. So that's 60 per 75. 60 per, 60 out of, or 60 in 75. And then we can reduce that. That'll be, what's 60? 5 times 12? 60. And 12 is 3 times 4. So 5 times 3 times 4. I could go further and do 2 times 2, but the denominator doesn't have any 2's in it. So 75 is 5 times 5 times 3. Yeah. 5 times 5 is 25. And then 25 times 3 is 75. Now, if the denominator had any 2's in it, then I would have gone a little further and simplified the 4 to 2 times 2. So I can cancel a pair of 5's and a pair of 3's. And the ratio is 4 calories. Got to write it now. Put the words back in 5 minutes. Yeah, so this would be like if I was on my exercise bike for 5 minutes. I burned 4 calories. That's the rate at which I'm burning calories, I hope. Or if I'm eating, I guess, because that didn't say whether I'm losing these calories or gaining these calories. It's just an abstract, rate. But I mean, I guess you could always think about it on the other side of the coin, right? I mean, I could be eating and I consumed 4 calories in 5 minutes, right? That'd probably be very slow eating, right? 5 minutes to only consume 4 calories. Either that or I'm eating, celery or something. I don't know. Maybe I'm hungry. I don't know what's going on. Okay. Let's see. Let's do another one. That's what I really need to get in the habit of doing is I always forget what value I'm on. 15 feet in 20 seconds. So 15 feet, 20 seconds. Temporarily ignore the units, so we do our scratch work. 3 times 5, 4 times 5, that was pretty quick. And then put the units back in. 3 feet per 4 seconds. So you might have noticed something about rates. It doesn't really kind of tell you how fast it's actually going, right? I mean, it tells you, yeah, in 4 seconds you go 3 feet. I mean, it does tell you that, but that's not typically the way we think about a rate, right? Most human beings, when you think about a rate, think about it. You get in your car, right? And you're talking, how fast are you driving? You're not going to say, I'm driving, 80 miles in 4 hours, or that would be pretty slow, but you're not going to say that, right? I mean, I guess you could, right? If you went from Palm Springs to, Los Angeles or something, and I don't know if it's 80 miles, but maybe to a particular city, it's 80 miles, and it took you 4 hours, right? Because there was traffic. Then somebody could say, well, how fast did you drive? And you could say, oh man, traffic was terrible. 80 miles in 4 hours. I mean, that would be a rate, right? But that's not really the way we think about speed, right? When you think about a rate, a rate of speed, you think about how fast am I going in 1 hour, right? So that's called a unit rate. Yeah. A unit rate is a rate in which the value in the denominator is 1. Yeah? Uno. Yeah? Unit. Unus. It's Latin for 1. Or unum, pluribus unum. Okay, so most of the time when we're talking about a rate, we like to know how much a unit is. So example 10, find the unit rate . 630 miles for 72 hours. All right, so that's a long time. That's like 3 days. And I went 630 miles. Maybe I'm riding a bike or something. Yeah. So the unit rate, you can just divide it. 630 divided by 72. 630 miles divided by 72 hours is 8.75 over 1 miles in 1 hour. Now, I know it sounds silly to say 1 hours. Makes it sound like you're, 5. But unfortunately, with the spelling and typing, you do have to say hours, but most of us would just say miles per hour. Yeah. So that would be 8.75 mph. Yeah, miles per hour, or miles per hours, even though the denominator is 1. When the denominator is 1, we just don't write it. So we omit the 1 from the bottom. That's pretty slow, 8.75 miles per hour. That's, like riding a bike very slowly, or very casually riding a bike. I certainly couldn't walk 8.75 miles an hour. I might be able to run that fast, but I mean, I'm not a long distance runner. I don't know if I could keep that up for 72 hours. So. It's more like a bike ride. So another unit rate that you probably deal with quite a bit is your rate of pay. Or what's called the hourly pay rate. In this example, I'm doing the hourly pay rate. So suppose you got a check for $273 for working 28 hours. All right. Now, I'm not going to get into the taxes and the withholdings and all of that stuff. in chapter 6, coming pretty soon, we'll get into that. It gets a little more complicated. Let's just assume that everything is just under the table here. You're just being paid $273 in cash, and you've worked 28 hours, and we want to figure out how much you're getting paid per hour. Okay, so the unit rate or the pay rate would be, well, it'd be the $273. I'm going to write it out just like it would look on the homework. We'd probably use the word dollars per, right, divided by 28 hours. Okay. You could do this if you have to with a calculator. I'm kind of towards the end, and probably a lot more in the next chapter I'll be doing a calculator, but this one actually isn't so bad. 273 divided by 28. Let's just practice our old school division here. 28 goes into 273 9 times. I'm just guessing. I know it's not 10, right? Because 27 is smaller than 28, so I'm going 9. 9 times 8 is 72. Carry the 7. 9 times 2, 18 plus 7 is 25. I might regret this if I make a mistake, and I'll wish I have this just in case. Let's see, so 3 minus 2 is 1, and 21. Let's add a decimal point. 28 goes into 210 about 7 times. 7 times 8 is 7 times 8. 7 times 8 is 56. Carry the 5. 7 times 2 is 14 plus 5 is 19. Subtract, you're going to get 14. Put another 0, bring it down. 28 goes into 140 5 times. 5 times 8 is 40, carry the 4. 5 times 2 is 10 plus 4 is exactly. Nice, I love that when that happens. You can see I get a nice remainder of 0 down here. All right, so your hourly pay of rate is $9.75 per 1 hour. Yeah, or I could say 1 hours, even though it sounds funny. And I'm just going to put it in standard form, which is the $sign, $9.75 per hour. So your hourly rate of pay, or your unit rate, the unit is hours. So there's your unit right there. So we're measuring this with hours. You can also do a unit rate of dollars per week. You have a weekly pay rate. Or you could do a bi-weekly, and every 2 weeks you get a paycheck, every other Friday or something like that. Or in my particular profession, we get paid once a month. So most teachers get paid once a month. So we have a monthly pay rate. You could also have an annual pay rate, although that'd be a long time to wait for your check. But you could have like an annual pay rate that's divided by 12 or something like that. And then that would, of course, translate into a monthly pay rate. So I'll give a few more examples. I'm not going to do every possible, time interval. But probably the most common one is hourly. So you got 2681, 7 weeks. 2681 divided by 7. Perfect. $383 per 1 week. Or 1 weeks. I know it sounds silly, but... And so that would be $383 per week. And so on and so forth. You could do this for months. How much do you get paid per month? Or you could do this per year. How much you get paid per year? Those are different types of pay rates. I think the most common is probably hourly, weekly, monthly, and then yearly. I've never heard of another one. I guess some people are bi-weekly. That's another way to do it, but unfortunately, the most common is probably hourly. Yeah, it's a sad state, but it's true. Okay. What's another type of rate that we see a lot in life? I like to use real-world rates that you might see. The fuel efficiency rate. Okay. So if I use 10 gallons of gas to drive 450 miles, you probably do this with mental math, right? It's 45, right? But I'm going to show the whole thing. It's 450 miles per 10 gallons. 450, I don't even need the calculator for that. 450 divided by 10 is 45. And that is MPG, miles per 1 gallon. And so we call that MPG, miles per gallon. 45 miles per gallon. And finally, the last type of rate. I mean, there's millions and millions of types, but the most common are the ones you deal with all the time. So how much are you getting paid? How fast are you going? How is your efficiency rate? Interesting fun fact. Trains measure fuel efficiency in GPM, gallons per mile. Completely upside down of the way a car would measure it, or cars usually miles per gallon, but trains, they use a lot of gas, right? If you ever see a big train, you see the big engine, half of it's the engine, the other half is a giant gas tank. And they carry thousands of gallons of gas to only go, hundreds of miles. So it's gallons per mile. And I have an example here. Suppose I use 524 gallons in 81 miles. I'm just going to do 80 miles so it comes out nicer. So the fuel efficiency is 524 gallons. I'm just going to abbreviate gal over 80 mi, just while I'm doing the math. 524 divided by 80 is 6.55 GPM. 6.55 gallons per mile. That's not very good. But it is what it is. This is actually a relatively normal rate. So when you see that train going down the tracks along the side of the freeway, every mile. Now, I just made these numbers up, but they're pretty close to reality. I made them up, but I made them up with a reasonable value here. And so to go 1 mile, they're burning a little over 6.5 gallons per mile. Well, they have to pay for that, right? They have to pay for this gas. It's not free. And so that's the final type of rate called price rate. Or unit price. So the unit price is the unit rate of price. So suppose I bought 8 ounces of, liquid. I don't know. I guess this is not a fluid ounce, so this is an actual ounce. So suppose about 8 ounces of whatever, some product that I'm buying, and I spent $7.39 on this 8 ounces. We usually round to the nearest cent. Unless it's gas. I think I was just talking about gas, but I think it's not going to happen until the next section where I talk really in detail about gas. I think for this lesson, I'm just talking about like products at the store. I mean, gas is still a product at the store, but I come back to it later. So, I mean, this very well could be a gallon, 8 gallons for $7. That'd be pretty cheap gas. Okay, so the unit price, again, you always have to put the price in the numerator. Always. Otherwise, it's not a price. So $7.39 divided by 8 is 0.92375. Okay. Again, technically it's over 1. Yeah. And you're going to round this to the nearest cent. So this is your rounding, and so this is your dictator. Yeah. That's less than 5, so we're going to throw all those digits away, and we're going to say our price is 92 cents or 92 hundredths of a dollar. And I'll just use the dollar sign per. This is per ounce. And then usually we drop the S and we write per ounce. You could also just say it in words, 92 cents per ounce. OZ is the typical abbreviation for an ounce. Unless it's a liquid. If it's a liquid, we do fluid ounces, but it's not really that big of a deal right now. Okay. Suppose it's, again, find the unit price. 4 pounds for $32. Well, that would be 32 over 4 pounds. Yeah. So that's 32 divided by 4, which is 8. I don't even need the calculator for that. And then that would be 8 dollars per pound. LB is the abbreviation for pound. Again, it comes from Latin or Libra. Yeah. So LB, Libra, pound. So $8 per pound. Remember, per is the slash like that. Usually with prices, we put it at an angle. I mean, you could put it horizontally. It just kind of looks funny. $8 LB. I mean, that's technically what this means, but it just looks funny. Sometimes we actually write the entire word, pound. There's really no standard. It's just whatever the given problem has you do. Okay, so the last thing today, well, this went by pretty quick. We're done with chapter 5 now, I think. Yeah, we're done with chapter 5. We're going to start chapter 6. I'm going to go right into chapter 6. So this kind of very end of chapter 5 and the beginning of chapter 6 are going to butt up right next to each other. This is what's called the best buy or the better buy. better buy or the best buy. That's where the store got its name from. So suppose there's two products. Product A, 26 fluid ounces, FLOZ, of, I don't know, soap or something, for $2.18. And product B, 36 ounces, fluid ounces of soap. Now I'm assuming it's the same soap. I mean, because otherwise you could argue, well, if it's not a better buy, if you're getting a worse product. So assuming it's the same soap, 36 fluid ounces for $4.10. I will mention when you read these, sometimes when something ends in a zero, the computer doesn't write the zero. I've tried time and time again to get it to do that, and the amount of effort I have to put into that is not worth it, so I just let it be. Occasionally you'll see a price like that, and you go, oh, what the heck's that mean? So if there is no second decimal point digit, assume it's a zero. So this is maybe the way it would look on the screen, and then I would just add in the zero, $4.10. My mother, when I was a kid, was an expert at this. I don't know about you, but when I was little, I used to ride in the, I'm talking little, 3, 4, 5 years old, whatever. I guess by the time I got to be 5, I was probably too big. But you ride in the little basket on the shopping buggy, and you're looking at the prices, and some people just have an innate ability to look at the two products. You might already know which product is a better buy. I like to use capital B. And it's definitely product A, right? I can see it, right? You have just an innate sense, right? So let's see the unit price or the unit rate for product A. Product A would be what? $2.18 for 26 fluid ounces. So that's 218 divided by 26. So this is dollars per ounce or fluid ounce. FLOZ. There are some dots there, but when you're just writing fast, you could do that. And then B, the unit price is, now I usually keep all the decimals because if I round it now, sometimes they come out to be the same and then it's hard to tell which one's the better buy. So that would be $4.10 for 36 ounces. $4.10 divided by 36. Yeah, that's way more. So this one's about 11 cents. So I'm going to do the squiggly. So I usually round these. So that would be 8 cents per ounce if you round it. And then this one would be the squiggle means I've rounded it, 11 cents per ounce. And so clearly the better buy is product A. Yeah, it's the better deal. Why don't I do one more just to end on a nice even number, and I'll do one where the values hopefully come out a little bit closer. Okay, this one was pretty obvious that product A was the better buy. So last example, we'll be done. So 34 grams, we'll call this A, 34 grams for $9.08, or 52 grams for $12.51. Never seen a price like that, 51 cents, but whatever. Okay. So again, I can't tell. Like I said, my mother could tell immediately. It's B, right? B's the better deal, right? Without even really doing the math, just instant. It's like she had a feeling, and the feeling was always right. $9.08 divided by 34. I hope these come out close. Divided by 34. So this one comes out to 26, almost 27 dollars per gram. G for gram. So that's A. B is $12.51 for 52. $12.51 divided by 52. It's a little closer. That's 24 cents per ounce. Or per gram. G for gram. Okay. Now we usually round to the nearest cent. So we already know that B is the best buy. We can already tell. It's going to be B. Yeah. 24 cents versus 26 cents. But I still want you to get the final answer right, other than just which one's best. So you're going to go to the nearest cent. And then you have your dictator. The dictator is the third decimal place. So that's going to go up to 27 cents per gram. All right. And then you throw away all these digits, and then you add 1 to the 6. All right. And then for this one, the nearest cent is 24, and then the dictator is 0. So we're just going to throw those away, and we're just going to get 24 cents per gram. And so the better buy is clearly product, oh, I pointed to the wrong one. Clearly product B is the better buy. Okay, wow. I feel so satisfied that we got through the chapter. I did have to skip one section. Don't worry, you're not missing out on your education. It's actually something that's not even listed in the description of this course, just kind of an offshoot section. So we are done with chapter 5. Got it in under an hour. That rarely ever happens with me. You know how I have a tendency to go on and on and on. But you know, I'd rather be over explaining than under explaining, hopefully for your benefit. I don't know what else to say. Until we meet again, this is Dr. Jordan. I'll see you on the internet.